All right, so we are starting the last homework 5 for process dynamics and control. Starting off with the first part of part A, we will be showing algebraically that the amplitude ratio and phase lag, the things that we've kind of derived, and we also coded into Colab in the previous homework of two transfer functions that we'll go ahead and draw out in just a second in series, which are the product and sum of the amplitude ratios and phase lags of the individual transfer functions respectively. Okay, so I'll go ahead and first draw out what the two transfer functions are respectively, and we're going to be referring to the first one as G1 and the second one as G2. One thing to know that is because it's in series, essentially these two transfer functions are going to be multiplied by each other. So we can kind of just write it out as G1, G2. And that kind of comes into play when we're specifically looking at our real and imaginary uh, when we look at the real and imaginary transfer functions, which are essentially components of each other. But looking at our first transfer functions and our second transfer functions, respectively to real and imaginary components, we'll write this out like this, which will look like for our first transfer function. R1 plus I1, so real plus imaginary, multiplied by our J function, and that's the first one. And this is going to be multiplied by our second transfer function, or G2, which would be R2 plus I2, J. Okay, so another way, so now what we want to do is essentially multiply these together, but like distribute it out and multiply it out. And what we'll get is this will equal R1, R2 plus, and we're going to kind of group them together so we can like multiply it by J and then kind of remove some of the I's out at the end, but it will look like R1, I2 plus R2, I1 multiplied by J. And then the very last part will be subtracted by I1, I2. Okay, so essentially we're going to be using this equation or formula. I know we're not supposed to say that, but we're going to be using this right here to get our amplitude ratio. And our amplitude ratio is essentially going to be squared. So when we look at it, it's going to be, there's not going to be too much space when I'm writing this out because these are going to be pretty long, but our first kind of fraction or derivation for this is going to be in our square root is R1, R2 minus I1, I2. And then this right here is going to be squared. And then it's going to be added by R1, I2 plus R2, I1. And then again, this is going to be squared right here. Okay, so now what we're looking at is what we want to do is essentially expand this out. And what we get here is it's going to look a little long, but I'm going to try to write as small as possible. Um, There you go. Okay, so what it's going to look like expanded out is R1 squared R2 squared minus 2 uh 2 R1, yeah, 2 minus 2 R1 minus 2 R1 I squared I1 and then R2. Yep. And then this will be added by I1 squared I2 squared. And then we're going to be adding kind of that same thing we had right here with the 2 plus 2 R1 I squared, I1, and R2. And then try to give us a little more space. And then we'll add R1 squared, I2 squared. Okay. So, of course, looking at this, we can see that we can cancel out some things. So I'm gonna go ahead and do that and then rewrite it. So this will go away. And then for our rewritten version for our amplitude ratio, what we'll get is R1 squared R2 squared plus I1 squared R2 squared Yeah, and then plus oh, I think I messed this up here. It's supposed to be r squared. And then what we get is plus r1 squared I2 squared. Yeah, that looks a lot better. That looks right. Okay, so from this point, we can look essentially at our tangent of phi. And what we know from this is tangent of phi, when we're looking at this respective to our tangent, what we get is no, sorry, I1 r squared plus R1 I squared uh, divide or over R1 r squared minus I1 I squared. And essentially, this is going to be uh, equal to I1 over R1. So essentially now we can look at this at our phases of transfer functions separately. But one thing to know before is if we're looking at tangent phi, we also know, let's say give an example, if we're looking at this at tangent phi 2, respective to maybe like a second component, it would be I2 over R2. All right. So if you kind of put these two together, so this one and this one, what we can see is that phi is going to be equal to phi 1 plus phi squared. And the reason why I talk about this is because it will essentially come back when we're looking at tangent and when we're looking at these kind of identity properties and combining them. Okay, so now let's look at this respective to tangent but with phi 1 and phi 2 combined. So doing that we get tangent phi 1 plus phi 2 using essentially sine and cosine because if you look at what tangent is, it's essentially sine over cosine, right? So when we look at this respective to sine and cosine, what we get is sine phi 1 plus phi 2 over cosine phi 1 plus phi 2. Okay, so expanding this out, we want to essentially use trig identities and expand all of this out. What we'll get is sine phi 1 times cosine phi 2 plus sine phi 2 multiplied by cosine phi 1. And this will be over cosine phi 1 cosine phi 2 minus sine phi 1 sine phi 2. Okay? So looking at this essentially into a more expanded version in essentially a more simplified version using tangent, what we get is this is going to be equal to tangent phi 1 plus tangent phi 2 over will be 1 minus tangent phi 1 multiplied by tangent phi 2. Okay? So we want to rewrite these we want to essentially rewrite what we kind of saw for earlier. So these tangent phi 1 plus phi 2 referencing real and imaginary components. Doing that, what we get is I1 over R1 plus I2 over R2 over 1 minus I1 multiplied by I2 divided by R1 times R2. Okay. Um, okay, so we're almost there, finishing this out. And of course, we have a fraction on the bottom, so we want to kind of multiply that out. And doing that, just cleaning it up a little bit, we get this will end up equaling R1, no, sorry, R2 I1 plus R1 I2 over R1 R2 minus I1 I2. And essentially, this is going to be our final equation. Going back and looking at the problem statement, we are essentially showing algebraically that the amplitude ratio, that's what we were looking at, and phase lag of two transfer function series are the product and sum of the amplitude ratios and phase lags of the individual transfer functions, respectively. So, okay, that looks good. All right, so starting the second part of part A, we will be showing algebraically that the phase lag of a first order system asymptotically approaches 90 degrees. Okay, so starting with this, what we'll want to look at initially is that essentially the equation that we've kind of worked on in other parts, which is kind of essentially our phase, which is K over uh, tau s plus 1. And essentially, K is our gain of our system. And this tau is essentially our time constant. One thing we can do from this is make a substitution for S in this case. We've done this previously as well, where we substitute S for J omega. So let's go ahead and do that. And what we'll get is K over K, which is our gain, over tau JW, so J omega plus 1. Okay. So from this point, this is essentially a force order system. What we will want to do next, before looking at our amplitude ratio, is multiply this by our complex conjugate. Multiplying it by our complex conjugate, what we get is K out on the outside multiplied by 1 minus tau J omega over 1 plus omega squared tau squared. Okay, let me just make this look a little pretty, but my handwriting's bad. So what we want to look at now essentially is our amplitude ratio. Our amplitude ratio for this function right here will look like this. And again, we're looking at a square root essentially. And again, this is going to be our k pulled out once again. And on our top, inside the quadratic, the square root essentially will be 1 squared plus omega squared times tau squared. And this will all be over 1 squared plus omega squared multiplied by tau squared. Okay, so simplifying this just a tad bit more, what we'll get is this will be equal to k multiplied by 1 plus omega squared times tau squared. And we're essentially kind of crossing out terms. We have similar things on the top and bottom, and removing our square root, we'll put this to the power essentially of negative 1/2. And so from this point, yeah, so similar numerator denominator, we can kind of cross it out, and then we'll get this. From this point, we want to look at the phase of the system. And looking at the phase, we're going to essentially be starting with phi, and phi is going to be equal to the inverse tangent of, on the top, what we'll get is um, negative tau omega divided by 1 plus omega squared times tau squared multiplied by k. And on the bottom, we'll get 1 divided by 1 plus omega squared times tau squared, and again multiplied by k. Okay? So from this point forward, what we can kind of deduce from this is we can cross out some things. And besides that, we also see kind of like terms. Have the 1 divided by 1 plus the omega squared times tau squared, and we have 1 plus omega squared times tau squared on the top. So from this, what we'll get essentially is our overall phase, which is our inverse tangent of negative tau omega. Kind of some things to look at from this. Um, we can see that as our omega goes to a very large number or infinity, our inverse tan of tau omega will essentially approach negative pi over 2, Yeah, negative pi over 2. But essentially what we're trying to get, if you look at this problem statement, is a system, a first order system that approaches 90 degrees. Now, how do we negative 90 degrees? Well, how do we get that? Essentially, this is in radian. So we can kind of know that we can essentially kind of convert it to degrees. So when so essentially phi will approach negative 90 degrees, which is converted from radian to degrees. Okay. Yeah, that sums that up. We've got this. Now we can go ahead and move on to part three. All right, so starting part three of homework five, process dynamics, we will be showing algebraically that two first order systems in series will always yield an overdamped second order system. So just some things to kind of know for first order systems in series, essentially when we're kind of referring to um, our transfer functions are when they're in series, they are multiplied together. So to kind of show how that comes into play. Starting with our transfer function g in the Laplace domain, this is essentially a first order. And again, this is going to equal the equation that we've been looking at, which is our gain. We're going to put this in terms of 1. So G1, K1. This is our gain over tau 1 S plus 1. And now let's go ahead and look at our second transfer function. We're looking at two first order systems, and this is again in the Laplace domain. And then we're going to be looking at our gain in the for our second function, and then tau squared and s plus 1. Okay. So essentially, like I mentioned in just a few moments ago, uh, transfer functions that or transfer functions first order systems in series will essentially multiply together. And when we do that, we're looking at G1 multiplied by G2. And combining these terms, we get K1 times K2 over tau 1s plus 1 multiplied by tau 2s plus 1. Okay. So what we can do now essentially is expand our denominator. And doing that, we get, of course, on the top the same K1 times K2 over tau 1 times tau 2 multiplied by S2. And then just combining some terms, we get plus tau 1 plus tau 2 multiplied by S, and then again plus 1. Okay. Some things to deduce from this is, as you can see on the bottom, this kind of looks similar to something we've learned in the past, right? And firsthand, you probably wouldn't notice, but of course, I've looked at this before, and that bottom fraction is actually follows a basic quadratic formula, essentially. That quadratic formula, for an example, is ax or a2x plus bx plus c. Okay, go back to my and then so some things is we will be looking for this quadratic formula, we will be looking at a discriminant. What a discriminant is, I'll get into it in a second and kind of how it comes to play with the our transfer functions, but this discriminative is what is of our quadratic to determine damping is what we call it. And for our discriminant, it will look like b squared minus 4ac. Okay, so go ahead and pause this. Okay, so from this we can finally look at our discriminant. Go ahead and okay, so finally looking at our discriminant, we're gonna get our discriminant, which is that kind of sign right there, which will equal tau 1 plus tau 2 squared minus, again, we're looking at this term 4 right here. This is our B term essentially, and we're looking at minus 4 AC, so tau 1 times tau 2, so essentially gonna be our A and C respectively. Um, yeah, so from this we can go ahead and simplify some things. So essentially we know that this term, this B term, tau 1 plus tau 2 squared is greater than or equal to 0, or it has to be. So from this, then we know that tau, our discriminant, sorry, is greater than or equal to 0. And essentially, this is a real and distinct route. This is a real and distinct route. So our system is essentially overdamped. Go ahead and back and looking at this, we want to show how two first order systems series will yield an overdamped second order system. Essentially, this is how when this term essentially right here is greater than or equal to 0, making our discriminant greater than or equal to 0, yielding in a real and distinct route. So our system is essentially overdamped, to put it in simple terms. Okay, so that completes part 3. All right, so starting the fourth part of part A for homework 5, we'll be deriving algebraically the phase lag for a pure time delay transfer function. So starting with the overall system kind of equation for this, um, this will be K, which is essentially our gain coefficient. And then this will be over our tau squared S squared plus 2 delta, which is our damping factor, multiplied by tau S plus 1. Okay, so looking at this, we can go ahead and see that there is another way to rewrite this. We've looked at quite a few times that S, essentially our Laplace domain function or factor, can be rewritten as j omega. So rewriting that, what we get is K over tau squared, um, tau squared. I'm trying to see if we need an omega here. No. Okay, we're good. So omega squared plus hmm. No, so we want to rewrite this a little bit differently to kind of move our 1 around, which will be 1 minus tau squared multiplied by omega squared. And then this will be added by 2 times our delta damping factor multiplied by tau j omega. Okay, so kind of just distributing this out a little bit, especially for specifically our denominator, we're gonna go ahead and multiply our uh denominators out, as well as calling in our complex conjugates. What we get from this essentially is what we get from this is K, putting that essentially on the outside, and then we'll get 1 minus tau squared multiplied by omega squared minus 2 delta tau j omega. And then that will be our numerator. And for our denominator, we're multiplying out our denominator out, right? So this is essentially going to be 1 minus tau squared multiplied by omega squared. And then this will all be squared plus 4 delta, again, that damping factor, multiplied by tau squared omega squared. Okay, so now from this, we want to kind of take the amplitude, we want to take our amplitude ratio. Sorry, give me 1 second. We want to take our amplitude ratio of this function. So again, we're using our square root kind of function here. So it's going to be k. And inside this, let's go ahead and look at our denominator. We're going to put that into here. So 1 minus tau squared omega squared. This will be squared plus 4 delta tau squared omega squared. Okay. So for our denominator is going to look essentially the same thing, which will just be 1 minus uh, tau squared times omega squared plus 4 delta tau squared omega squared. Okay, so now we can go ahead and kind of simplify this out a little bit, kind of taking out our K and seeing that we have a lot of like terms here. So we can go ahead and put this K out, and what we'll get here is 1 minus tau squared times omega squared. All of this is squared. Change. Nah, that's better. Okay. Times yeah, all that squared plus 4 delta squared, tau squared, omega squared, and this whole function squared. Okay. So now from this point, we can kind of go ahead and look at our phase lag and take a derivative of our amplitude ratio. Doing that, we are taking the derivative of our amplitude ratio, however, with respect to omega. So doing this, what we get is because we're looking at essentially a quadratic and taking the derivative of that, we have negative 1/2. Go ahead and pause this. Okay, so we get negative 1/2 times k, which is essentially just our constant here, multiplied by 2 times negative 2 tau squared times omega, multiplied again by 1 minus tau squared omega squared plus 8 delta squared minus tau squared omega. And then this will all be over, this will all be over 1 minus tau squared omega squared, all of this squared plus 4 delta damping factors squared tau squared omega squared. And then again, since this is top is going to be to the power of negative 1/2, for our bottom denominator, this is going to just be 3/2. So we can now go ahead, kind of getting close to the end here. We can go ahead and find the max. So we're gonna go ahead and try to find the max of our amplitude ratio with this function. So we want to go ahead and set our denominator to 0, or set our function to 0. And doing that, we get 4 tau squared times omega multiplied by 2 delta squared minus 1 minus tau squared times omega squared. Okay. All right. So from this, we can see that the system has no damping essentially because our delta or damping factor is equal to 0. So if our delta damping factor is equal to 0, then we'll have our omega equal 1 over tau, which gives us essentially a max amplitude ratio. Okay. So, yep, that's essentially our final, this kind of sums it up regarding our max amplitude ratio. Let's go ahead and make sure I didn't miss anything. Yeah. Okay. So we're going to go ahead and move on to part 5. All right, so finishing off part A of homework 5, we're gonna go ahead and we're gonna go and show and explain how a first order system with time delay may become unstable with proportional only control. So looking at this, I'm gonna go ahead and draw an XY diagram, and let's say we kind of have a system or kind of a um exponential function that kind of decays but then increases right here, right? So let's just keep it at that. Um, and let's say we kind of want to introduce a new equation that fits this model using our time delay, essentially. So let's give that for an example and give an equation where we have time delay. So we'll have essentially something that will eventually exponentially fit our equation like this. So kind of increase the thickness for this. So kind of go like this, and then we want it eventually to fit our graph and exponentially fit that line, and that equation will kind of go up, and then it'll eventually kind of go along that same route that the old equation does. However, this is the new equation with their time delay, right? There's just time delay, and then eventually it fits our equation. Okay, so let's go back. Um, essentially we want to derive an equation for this, right? So we're going to go ahead and start with K, which is essentially our gain. And then we have our E kind of factor to the negative of our time delay, essentially, or phi times S, which is essentially our Laplace domain. And this will be over tau S plus 1. Okay, so from this, we can kind of look at specifically this right here. And looking at that, we can see that this can be kind of rewritten in a few different ways, right? The first way will essentially be this factor to the power of negative phi. And let's guess what it'll turn to. S is equal to j times omega, right? So let's just go ahead and put that in there. Again, though, we can rewrite this in another way, right? We've been looking at identity properties, so we're going to be looking at sine and cosine for this. So this is going to be equivalent to cosine with our time delay phi omega minus j sine omega, oh, phi omega. Okay, so we want to go ahead and take a look at our amplitude ratio now, right? So looking at this, essentially this right here, we can see that our amplitude ratio is equal to cosine squared phi plus sine phi, okay? And then essentially this is equal to 1 because of these properties of cosine and sine, essentially. All right, from this, we can go ahead and look at our phase lag essentially. So kind of looking at our time delay phi coefficient, we will have our time delay equal to the inverse of tan of, excuse me, of sine, negative sine phi omega over cosine phi omega. And one thing to note from this is sine over cosine, we're looking at tangent. So we already have tangent in this problem, so it's gonna kind of be a repetitive form of tangent and tangent, but it'll be the inverse of tangent again of phi omega. We still have these terms here. We have this term, which is tan. So this will be looking like this. And essentially we can go ahead and kind of cancel these things out, right? We have tan and tan. So we're going to be left with negative phi omega. So essentially this is kind of our end result. This is what we wanted to essentially be derived. But let's go ahead and see when we kind of plug it back into this equation right here. So you have tan inverse tan of tau omega minus phi omega, right? So this is essentially our phase lag that will give us linearization. So essentially with higher frequencies, phase lags will be kind of greater than our overall system. And kind of take it for an example of our last problem that we did when kind of goes from 0 to negative 90 degrees, right? We had a kind of a situation where we were trying to obtain a 90-degree uh, kind of goal, right? But however, with this case, with our phase lag, because of its linearization, we can actually go straight to infinity or a substantially long, really long number, right? So yeah, that pretty much sums up how this first order system with time delay may become unstable. And yeah, proportional only control. So that kind of comes back to how we introduce these terms of omega and our time delay and how that is only applicable to when we have proportional only control. So yeah, that completes uh, our part A for homework 5. So we can go ahead and move on to part B.